Hi and welcome back. Okay, it feels like we've not made much progress on this build for a little while because of the trouble we had that I then spent an additional video troubleshooting, but everything's working again now. So let's actually make some progress. Now when it all started to go wrong, we were looking at controlling the transfer bus that connects the 16-bit registers. Let's have a quick reminder of where we're at. Now, we connected up the increments and the decrements to the counters. So we've got some test code in here which will do an increment, and another increment. And then we run through a succession of decrements and then go off and do some stuff with the general purpose registers. And we've added these demultiplexers which are controlling which of the counter address registers asserts to the transfer bus and load off it. And these are connected up to these little lines up here. So if I bring this line high, I'm now asserting the program counter to the bus, and then I could tell one of the other ones to load. So let's go with 4. So now when I clock it, the contents of the program counter should get loaded up here. These lines are just kind of manually held to the ground or 5-volt rail, and we need to get them over into the control unit. Now those lines are going to go into pipeline stage 1. So we've got a total of 16 control lines here, and I would like to avoid expanding it out any further than that. So let's look at what we've currently got. There are 4 control lines here that select the LHS and RHS inputs into the ALU. We've also got 2 lines here which are kind of temporary. They go into the ALU to select what the shift unit is doing. An unused line, we've got the constant load line, and we've got these 3 lines which are currently selecting decrement. So we've got 5, 6 spare lines at the moment, and that's exactly how many lines we've got up here. But there is additional work to go in there. So I want to start looking at doing some combining and saving of the control lines. Now, it does occur to me that we don't have a usage case in the plan for the processor where we both decrement a register and load a 16-bit register in the same operation. So we could actually combine these. So what I'm going to do is tie the 3 select inputs of those 2 sections together. Sorry, this is quite annoying. All these control lines are slumping over where I need to see. But what I'm just doing here is tying the address lines, the 3 address lines from the 138 that controls decrement to the 138 that controls loading from the transfer bus. So these 3 control lines are what's selecting that, and at the moment it's going to end up doing both operations simultaneously, which is not what we want. So I'm going to stick an additional line in which connects an active low enable with an active high enable. And if we use that as the 4th selection line, then we effectively have a upper control bit that will say whether or not we're doing a decrement or whether or not we're doing a load from the transfer bus. This is very similar to what we do for devices on the main 8-bit bus using a pair of 138s. In fact, the configuration is exactly the same. Although this is doing 2 different jobs, that's effectively still expanding that address range. So we can do that wherever we want, as long as we've accept that the 2 different jobs or more jobs that we're doing with that technique don't overlap, because we lose the ability to do them simultaneously. Now, so instead of these 3 control lines going across, we need 4 control lines. So then we've got these 3 control lines on the second 138, which are controlling which value is asserting to the bus. Once again, we can put that into pipeline stage 1. Now, when we wired up the decrements, we didn't use position 0, because that was going to be our neutral. But now, because of the way we wired this up, we have a neutral in both numerical ranges, and we only need one of those. We've got an extra option coming out of this 138 that we can use. We're only using 5 of the 8 at the moment. Up here we're going to be using 6 of the options because we want to be able to load the transfer register, but that register doesn't have increment or decrement, so we're never going to use it here. Now, this chip down here is unrelated to any of this discussion. This is taking the constant load line, and this control output goes directly into here in order to suppress passing an instruction through. So it stops the fetching, but it also goes through this NAND gate and outputs to the constant load. Now, something I'm interested in doing is kind of trying to keep the chip count down as low as possible. So the fact that we're only using one gate on this is kind of bugging me a little bit. There's also a case that I may get to in a few videos where I would be interested in a way of preventing a byte from turning into an instruction that's come from the instructions stream in the same way we do to divert it as a constant, but that wouldn't necessarily involve the constant register. So something I thought I could do is actually replace the logic chip here with a constant load with a bit of clever reuse of one of the spare lines we've got up here. So I appreciate this doesn't directly relate to the transfer bus, but we are going to be using one of the same chips for doing this work. And this is quite a small job which I've been kind of thinking about for a little while, and it wouldn't have made a video in its own right. So I'm going to change the fetch suppress line and put it in the topmost bit. So that's half the functionality that we previously had in the constant load. And then we're going to take the second half of it from the previously unused first output bit alongside the decrements. Let's look back at the processor definition and control code and see if we can get it all working. Now firstly, these decrements they've been shifted up by 8. So we need to add 8 to all of these entries in the enum. And we've additionally added a new entry in that section for loading the constant register. Now we no longer have this constant load, but we do have a no fetch control line, but we put that at the very top. And we've got the loads for all of our 16-bit registers. I'm going to put the define in for TX, even though that register doesn't exist yet. And we've also got the 3 lines we added for controlling what we're asserting to that transfer bus. And that's from bit 12 upwards in the control word. Right, and we need to add some instructions. Oh, let's fix the constant load first. Right, so previously we had this one control line called constant load. Now we need to request a constant load, and that merely tells the register to load, but we also want to output this new no fetch line to suppress fetching from the instruction stream. And that should have the same effect as before. Okay, let's get some use of the transfer bus in. Now we've got a total of 6 16-bit registers, and so the total number of movement permutations between them is going to be 6 times 5, so that's 30 potential move instructions we could add here. But some of those moves don't make so much sense, and 30 is actually, that's quite a big chunk of our total 256 possible instructions. So I think this is one of the first situations where we're going to have to look quite closely and say, what do we really need? So you've got a minimal set of moves which would allow us to actually get data around the place, and then you've got the exhaustive, this is every possible move we could encode onto the operations. So what I'd like to first think of is, what is the minimum set of moves? So if we have the ability to move everything into and out of one single common register, then all the other move possibilities could be done by moving things in and out of that one register. And I'm going to pick TX for that, because the transfer register is the register which allows us to move things between the 8 and the 16-bit sides of the register stack, and so that's quite an obvious one to use as an intermediary. Now, I don't see any reason for moving in and out of the program counter with a move instruction, but obviously we are going to have some flow control instructions that do that we'll add later. So that's the 4 remaining 16-bit registers being moved in and out of TX. And now let's think about other ones that might actually be handy. SP is the stack pointer, SI and DI are slightly more general purpose pointer registers or index registers. So I think we definitely want to be able to move between those. Yeah, I think that pretty much covers it. Now I'm expecting that the transfer register is going to be our primary store of a jump target, although it is a slight problem in that the transfer register doesn't exist at the moment. So let's add a second one in, although we're not expecting to keep it. Actually, I've got a better idea. Let's leave that as TX, but we can kind of fake the whole situation here by making our defines for load and assert TX actually just shadow the ones for DI. So we can write control code which makes reference to TX, and we're actually just going to use DI. So I don't see a need for more than one index pointer right now. And we're going to have the transfer register in a couple of weeks anyway, so that's just a good temporary way of testing things. Alright, so as before, we need to run the assembler, and that will read this architecture file in, and it will update our enum here. Here's all our new instructions. So now we need to look at what control lines we need to activate to implement each of these instructions. So just like we had on the 8-bit bus, this instruction is copying the contents of TX into RA. So we're going to assert TX onto the bus, and then we're going to instruct the return address to load from the bus. Right, so for a jump, here's what we're interested in doing, is we assert TX to the bus, and then we load program counter. So from a kind of a control perspective, is exactly the same as a move operation, only the destination of our move is the program counter. Right, let's write some test code. We don't have very many easy ways of getting interesting looking numbers into these registers, but let's pick a register and increment it a few times. And then we can move a copy of it into, let's go into DI. Yeah, and then let's deck DI a couple of times. Going to need to take advantage of the fact that DI is shadowed with the TX register at the moment. Might also want to do a constant load just to test that that's still working okay. Okay, so we need to update the program ROM and all 4 control ROMs. Actually, we haven't done anything that affects pipeline stage 2, so we only need to update the control ROMs for pipeline stage 1. Right, so the first instruction we've got in there is load A, 42 hex. Yes, so we've updated the operation of the constant load correctly. So then we've got free inc SIs. So this should go up to 3. Oh, sorry, this is SI. And then this was a mov di, SI. And that hasn't done what we wanted. Oh, hang on, program counter has got assert address on, and its last value was this. So that's copied the program counter into the DI register. So then we've got 2 decrement operations. And then we've got a move TX into SP, which is going to attempt to copy here to here. But our last move didn't work. But that one did. So it was the SI into DI that didn't work, right? Let's double check that. So the constant load already had that value in, so we didn't notice it. We've got our free increments. Ah, okay. Simplest of mistakes. I've got the assert lines in the wrong way around. It says SI being asserted. So there's our copy happened. I remember increment happens up here and the copy is happening here, so that the copy has actually received the state of the SI register 1 instruction before. So that's one of the little oddities about our pipeline processor. Things can happen simultaneously or slightly out of order, which is a penalty we pay for a simple yet fast architecture. So there's our 2 decrements, bring that back to 0. Yeah, and then the move TX into SP is going to do nothing now. The values are working. Okay, that's excellent. I believe that is the first time I've made a notable update to the control ROMs and had it all work first time. So this is a good sign for going forward. But hopefully you found this interesting. Next video, we're going to switch back to the ALU, I think. I'm very conscious that the transfer register over here is going to make a big difference to the total functionality that we have, but then the ALU is another one in that class as well. So those 2 sides of things are going to open up a lot of functionality, and I think naturally moving on to this one is the right thing to do. But thanks for watching. Goodbye.